using lattice field theory, supersymmetric theories on a lattice, and he also does traditional lattice QCD as well. So over to you, Georg.
Okay, thanks a lot, Anas, and thanks a lot for the invitation. It's a pleasure to present here my research topics. Since it's now a more broader audience, I will make a more general introduction on the topic, and then later on focus a little bit on the things that I've been working on. So the topic will be supersymmetry on the lattice, which means how we can put supersymmetric theories on a space-time lattice and what kind of problems we are facing. And then I will focus on N-1 supersymmetric Young list theory, basically because this is the theory that is most well studied and most well under control for in this case. But I will then also explain different kind of things that one can do to get beyond this and to investigate further theories. So the outline is the following. So the first two topics basically are introduction and basically an historic overview of this problem and what kind of things you have to face if you want to study supersymmetric theories on the lattice, the main obstacles, and also the open question that still remain in this respect. Then I will talk about the recent progress in that direction. So it has been going on has been going on over a few decades now. And the main numerical results that I'm going to present are concerning N=1 supersymmetric Young list theory, and these will show what to expect if you are able to investigate the theory on the lattice, what kind of interesting things you can investigate and study using these non-perturbative tools, and what kind of new insights you get for the theory. And then I have a few other topics, and depending on the time, I will then also cover the steps towards more general supersymmetric theories up to even N=4 super Young list theory, depending on what time is left. So let me first start with the question why we want to study supersymmetric theories on the lattice. And the main first motivation for this was to study beyond standard model physics, and in particular understand possible scenarios for supersymmetry breaking. And these kind of scenarios always require a kind of non-perturbative sector and investigations that allow to access the non-perturbative properties of the theories. And if you want to study this in general detail, then you need non-perturbative methods, and the most well-known methods are lattice computations. Later on, additional motivations arose. So one of them is that you have a lot of understanding of supersymmetric theories. So strongly interacting theories, supersymmetric gauge theories, can be studied much better analytically than their non-supersymmetric counterparts, just because of the additional symmetries that you have in this case. So the question is, how can you learn some lessons for non-supersymmetric theories, for the mechanism of confinement, etc., from these supersymmetric theories? And to study this, you need to have a non-perturbative tool like the Lattice provides to study deformations away from the supersymmetric limit. And then, of course, there's also gauge gravity duality, where you need to verify the prediction that you can derive from the gravity dual, or get insights from the gauge theories into quantum gravity. So it would be interesting to study supersymmetry on the lattice, but one faces several problems. First of all, there's a theoretical problem. can we realize supersymmetry on a discrete space-time lattice? And this is in particular difficult because supersymmetry is tied to the symmetries of space-time, since it relates fermion and bosonic particles, so particles of different spin. It's intimately tied to the symmetries of space-time. And more generally, you want to control the supersymmetry breaking if you cannot realize it on the lattice. If you have a recipe or a kind of control about the supersymmetry breaking on the lattice, then there is a second question which arises in this practical simulation. And it turns out that concerning the theoretical consideration, supersymmetric theories have very nice properties, but they do not work out so nicely if you apply numerical methods. So it's from the theoretical point of view and from the practical point of view, it's a rather difficult problem, and one has to face several obstacles. Concerning the practical simulations, I will present mainly supersymmetric Young-Mills theory, and I will discuss in the next part a little bit about the theoretical problems that you face if you want to realize supersymmetry on the lattice. If you just want to implement a supersymmetric theory on the lattice, you have to face a Nogo theorem that has been found quite a decade ago. So the problem there is that locality on the lattice contradicts with supersymmetry. So if you want to derive a supersymmetric action, you always have invariance up to total derivative terms, unless you have a trivial free theory. And this kind of total derivative terms are built up using the Leibniz rule of differentiation. And what you learn from the mathematical properties of the discrete derivative operators is that you cannot realize the Leibniz rule unless you implement a known local derivative operator. And in addition, you need some kind of known local product rule on the lattice. So this is a general problem. And then in addition to that, so this applies for any kind of non-trivial supersymmetric theory on the lattice. But then there are further problems which are related to the fact that you have a fermion doubling problem. So typically you have additional terms that you have to add to the derivative operators, which introduce additional mass terms for the fermions on the lattice. And since there are no bosonic counterparts for this doubling problem, then this leads to a mismatch of the mass terms in the supersymmetric action. And even more, if you consider the relation between supersymmetric relation that relates gauge fields to the fermion fields, then you have the problem that gauge fields are represented on the links of the lattice and not as the fermions on the side. So you would have to deal with this kind of problem if you want to implement supersymmetric lattice action. And this is a reason why very strict people even say that this is the reason why we don't observe supersymmetry, because it's not, it cannot be made brought on the lattice in a straightforward way, and therefore supersymmetry cannot exist in nature, because the lattice is the only viable non-perturbative definition of a quantum field theory. These are only a few people that make such a strict statement, but there might, of course, be some general problem where this points to this problem of realizing supersymmetry on the lattice. Now let us look at other symmetries. So actually the situation is quite similar to chirosymmetry on the lattice. There you have the Nielsen-Nomia theorem that also states that locality is in contradiction with chirosymmetry on the lattice, but there has been a way out in this case, which is the so-called Ginzburg-Wilson relation. It's a modified symmetry that is derived from randomization group arguments, and that tells you how to implement the symmetry on the lattice in order to recover the full symmetry in the continuum limit. So it is a kind of lattice version of the symmetry, or a controlled breaking of the symmetry on the lattice. Then you can also look at the symmetries of space-time, and there the lattice preserves a subgroup of the full symmetries of space-time, and this subgroup can show is enough to recover the full symmetry in the continuum limit. But this is not the case for supersymmetry. Now the question is whether we can derive something similar like the Ginzburg-Wilson relation also for supersymmetry, and one can generalize the Ginzburg-Wilson relation. Peter Hasenfratz has always told that the Mrs. Randomization group is a good physics teacher, and she teaches us how to implement symmetries on the lattice, and therefore one should use some Ginzburg-Wilson type realization on the lattice. And some time ago, we have derived a generalization of the Ginzburg-Wilson relation that applies for any kind of symmetry, and is derived also using some randomization group arguments. However, it's still an open problem to find solution for this rather complicated structure that you get in case of supersymmetry. And therefore, one has to say that we don't understand completely the lesson Mrs. Randomization group is telling us about this realization of supersymmetry on the lattice. So since we don't have such kind of a nice solution like a complete realization of supersymmetry on the lattice, or a Ginzburg-Wilson relation that ensures a restoration of complete supersymmetry, there can only be model-dependent solutions that we can use to approach the supersymmetric, to recover the supersymmetry in the continuum limit. And here I've sketched some solutions. So either you have the breaking under control, and you have a breaking at any finite lattice spacing, and it is recovered in the continuum limit. So what is shown here are, in a one-dimensional simple model, the word identities of supersymmetry. There are two supersymmetries and in this kind of theory, and therefore you have two word identities, and you see a small breaking, and this vanishes in the continuum limit if you have this breaking terms under control. So this is a kind of fine-tuning that you do to approach the correct continuum limit. Then in the second picture here, you see that one word identity is already zero at finite lattice spacing, and this is in some models with extended supersymmetry. It's possible to have these implement part of the supersymmetry on the lattice, and this helps to reduce the fine-tuning problem and recover the supersymmetry in the continuum limit. And then here in the last picture, you can see you can also have both word identities fulfilled at any finite lattice spacing, but the Nogo theorem then tells you that you have to implement a known local lattice action. And then you have to ensure somehow that the breaking of locality is not relevant in the continuum limit, which is also quite difficult to show in the general case. So the first studies have been done in that respect for one-dimensional models, and one can show that even in the one-dimensional case, if you look at these historical investigations, then you see that even in the one-dimensional case, the naive implementation of the supersymmetric theory on the lattice doesn't lead to the correct continuum limit. These are here the yellow and red lines, which show that in the continuum limit, the masses don't match each other, so you get a severe breaking of the symmetry in the continuum limit. But one can then implement additional actions with appropriate reformulation and counter terms that in such a way that you get a restored symmetry in the continuum limit, and even only a small breaking at a finite lattice spacing. And in that case, so in the one-dimensional case, you can even use known local lattice action, and in some two-dimensional models, this is also possible. And you can show that in that case, the breaking of the locality is not severe, and you get a local continuum limit. Then the other efforts are, of course, in several other directions. So interesting applications are in one- and two-dimensional matrix models as well, where you have the supersymmetry breaking under control, but there are interesting gauge gravity dualities even for these low-dimensional theories. So these can be studied on the lattice. And then there is in 4 dimensions the case of n=1 supersymmetric Young-Will theory that I will discuss in the following. And there you have only one fine-tuning parameter, and this can be easily controlled. There's additional work in 4D on n=4 supersymmetric Young-Will theory using a particular formulation that preserves part of the supersymmetries on the lattice. And in that way, one can ensure that you get the correct continuum limit, even for this 4-dimensional theory. And there are the more challenging parts I will maybe discuss a little bit in the end, and these are supersymmetric QCD and n=2 supersymmetric Young-Will theory in 4 dimensions. There have been some perturbative studies, and different attempts, but still there is a lot of work to do. So let me now start with supersymmetric Young-Will theory in 4 dimensions, n=1 supersymmetric Young-Will theory. The theory is actually very similar to QCD. The main difference is that you have fermions that are in the adjoined representation because they are partners of the gauge fields, and they are Majorana fermions. I've put here an additional mass terms for these gluino fields, so this has to be set to 0 in the supersymmetric limit, since there is no mass term, of course, for the gauge bosons, which are the supersymmetric partners. So motivations for studying this theory are, of course, as I said, the extensions of the standard model, but then there have also been some prediction of a controlled confinement in semi-classical regimes for these theories. And then there's a connection to QCD using orientifold planar equivalence. In addition, n=1 supersymmetric Young-Will theory is like the first step if you want to study other supersymmetric gauge theories, because it's a pure gauge part of these other theories. As I said, this gluino mass term leads to a soft supersymmetry breaking. An additional symmetry that you have in this theory is a U1R symmetry, kind of chirosymmetry. So in QCD, if you have fermions in the fundamental representation, this chirosymmetry would be broken by the anomaly, but in case of Majorana of adjoined fermions, you have a discrete subgroup that remains intact, and this is spontaneously broken then by the gluino condensate down to a Z2 symmetry. So there are NC different vacuas for the theories that are determined by the different values of the gluino condensate. Now, if you formulate this on the lattice, you can use kind of the standard techniques. And
can I ask a question?
Yes, of course.
So in the previous slide, there is no goldstone because the anomaly already breaks it to Z mod 2Cs.
Yes, yes.
Okay. Goldstino, I should have expected, right?
Goldstino are, so the Witten index is non-zero, so there can't be any supersymmetry breaking. So Goldstino refers to supersymmetry breaking, spontaneous supersymmetry breaking, and this cannot occur for this theory. This has been shown by Witten.
Yeah,
but of course, if you would have a continuous chirosymmetry, then you would have Goldstone modes as well.
Yeah. Okay. Thank
you. So we are using here Wilson clover fermions, which break the chirosymmetry of the theory, and of course, as I said, supersymmetry it's unavoidable to break supersymmetry on the lattice. This U1, this chirosymmetry has to be, both of these symmetry have to be recovered in the continuum limit. But the good thing is that there is only one parameter that you need to fine-tune both symmetries. So the breaking of chirosymmetry and the breaking of supersymmetry can be resolved in the continuum limit by tuning a single parameter, and this is the Gluino mass. There are even, if you consider fermions, Ginzburg-Wilson fermions, so that implement this modified chirosymmetry on the lattice that I've talked about, then you even need no fine-tuning at all to simulate supersymmetric gamma theory on the lattice, because this Ginzburg-Wilson relation ensures a complete supersymmetry in the continuum limit. You can use different methods to implement the fine-tuning and to study the breaking of chirosymmetry and supersymmetry in order to tune the mass parameter correctly. The nicest possibility would be, of course, supersymmetric ward identities, but these are relatively hard to measure, and you get a rather noisy signal. And therefore, what we have looked at is some kind of chirosymmetry breaking indication by an adjoined pion mass. So we discussed this already. So the pion is not really a physical particle because we don't have a continuous symmetry, but you can define it in a so-called partially quenched setup here. This pion mass, and you can still measure it and then determine the tuning of the mass parameters. And in the end, we always check that this is consistent also with the supersymmetric ward identities. So the first thing that you would like to study is, of course, whether the theory is consistent with supersymmetry on the lattice, or whether you have any kind of maybe even unexpected supersymmetry breaking in the non-perturbative regime for this theory. And the easiest way to do this is to verify that you have a degenerate multiplet of particles. And it's natural to expect that the lightest multiplet of the theory is just chiral multiplet. So it consists of scalar, pseudoscalar, and fermionic particle. The fermionic particle is what we call a gluino glue, and then for these scalar and pseudoscalar particles, you have different possibilities. So you can make them just by glue balls, or you can also consider mesonic states, and we in fact studied both of them. Here are also the operators that you implement on the lattice. So this gluino glue operator is a kind of non-standard operator that you have especially for these kind of theories with adjoined fermions. And the other things are more or less standard. You have similar observables for QCD, but what you know already is that these represent flavor singlet mesons, and these are also in QCD rather noisy measurements. In addition, you have to consider the fact that you have Majorana fermions instead of Dirac fermions, and therefore you have to implement in the simulations a Parthian of the Dirac operator, which you obtain when you integrate out these Majorana fermions. This is up to assign a square root of the determinant, but you have to take into account a mild sign problem that vanishes in fact in the continuum limit of the theory. And then you have to do a lot of extrapolations. So you have to extrapolate the chiral limit. This is a limit where the mass parameter is tuned to the correct value. And then you have to extrapolate this the values in this chiral limit also to the continuum limit in order to remove the lattice artifacts. And also you have to control the finite volume effects, etc. We've investigated SU2 superimage earlier, and we have also presented 2019 then our final results also for SU3 supersymmetric inverse theory. Here's just a comment concerning this simulation of the Parthian sign. So what we have to do in order to measure this is more for the experts. We have to measure a certain subset of the eigenvalues of the Dirac operator in order to determine the sign of the Parthian. And here are some results. So on the x-axis, you have this chirosymmetry breaking indicated by this adjoined pion mass. And then you have masses of different states. So you have the pseudo-scalar state. This is this blue one here. Then you have a scalar state and a gluino state. This is a fermion. They should become degenerate in the continuum limit, and increasing beta, you decrease the lattice spacing. And you see that more or less they come closer and closer together. You always have to consider this extrapolation here to zero chirosymmetry breaking. And this is then the results that you have to take into account. So you can take these results here and then extrapolate also to the continuum limit. And here is this shown as a function of the lattice spacing, showing two different kind of extrapolations, because we have an improved lattice action. We can even take just a squared here. And you see that they basically form nicely a multiplet of in the continuum limit. Note that the errors are rather large. This is due to the fact that, as I said, these are rather noisy quantities, which you already know from the experience with these QCD counterparts. So this shows.
Sorry, you have said this twice, but what is the meaning of a noisy operator from the point of view of a continuum description?
So noisy just means that if you have lattice simulations, you have to do statistical analysis. So you simulate the path integral using importance sampling, and there you have only a subset of the full configuration space, and then you have to do averages. And these observables here, they fluctuate rather a lot in these averages. So you get larger statistical errors.
So can I understand that from a continuum thing as some large anomalous dimensions or something like that?
No, well, it's rather difficult to explain this here, because it's in this case it's rather amounts to some kind of volume factor. So if you consider, for example, the pion mass, then you have an additional volume averaging, and this provides you a much smaller noise here.
I see.
So you can, in some cases, understand these errors from excited states as a similar channel in the continuum, which also leads to additional noise. But here it's rather that due to volume averaging, and also that for example, the glue ball operators are rather local objects, and they fluctuate therefore quite a lot.
Yeah, thank you.
Okay, so are there additional questions?
No, thank you.
Okay, so this shows that supersymmetry is recovered for this theory in the continuum limit, and that also you don't have an unexpected supersymmetry breaking in this theory. We have also investigated the supersymmetric word identities, and these confirm the correctness of the extrapolation, and also that you basically extrapolate to 0 in the continuum limit, which means the remnant supersymmetry breaking vanishes. Now, you want to study, of course, additional properties of the theory apart from the particle spectrum. And the second most important investigation are of course the phase transition, which are also generically non-perturbative properties of the theory. And the phase transition in supersymmetric Young-Mills theory can be compared to the supersymmetry to the breaking to the phase transitions in QCD. In QCD, you have the deconfinement transition and you have the chiral phase transition. And if you consider in QCD the physical quark masses, then both of these transitions are rather just crossovers, because center symmetry is broken by the fermions and the chiral symmetry is broken by the finite mass terms. So you only have in the extreme corners of very heavy quarks, you have the proper definition of the deconfinement transition. And then also for in the limit of vanishing quark mass, you have this region where you have also a well-defined chiral transition. And in between, you have just only a crossover. In supersymmetric Young-Mills theory, this is different. So you have intact center symmetry for any mass. And you have, in addition, if you go to the massless limit, which corresponds to the supersymmetric limit, also an intact chirosymmetry, and therefore you have two independent transitions. And you can now ask the proper question whether there's a relation between this deconfinement transition and the chiral transition. There are, of course, this question has been discussed also in QCD, but there it's not really a well-defined question because you have only a crossover for both of these. That's a physical point. And there are analytic predictions for this transition. So there's a strict prediction that the chiral transition should be above the deconfinement transition. This comes from 't-Hooft anomaly matching. And then there are conjectures from string theory that you even should have a saturation of this bound, that the chiral symmetry and the deconfinement symmetry should agree. In early investigations with adjoined fermions, there has been observed a large difference, in fact, of these chiral and deconfinement transition, but these have been investigations with a larger number of adjoined fermions, and it's not clear whether also the systematics have been under control for these kind of theories. So that's why we have started some study of the chiral and deconfinement transition in supersymmetric Young-Mills theory, and we found that up to our precision, which is rather rough here, considering the rather broad peaks of the susceptibility of the Polyakov loop and the chiral condensate that are shown here as indications of the transition, we have found that the chiral and the deconfinement transition agrees. And we were even able to compare the phase transition to pure Young-Mills theory. So this is kind of an interesting observation, when one can even go one step further and change the boundary conditions. So the thermal partition function on the lattice is represented by a implementation of the theory on a torus with boundary conditions that are periodic for bosons and antiperiodic for fermions. And if you now change to periodic boundary conditions for the fermions as well, then you don't break supersymmetry and you arrive at a twisted partition function. And this in supersymmetric endless theories, this represents what's called the Witten index. And as has already been predicted by Witten, this kind of partition function is continuous, and therefore you don't expect any kind of phase transition if you switch to periodic boundary conditions. And in that way, you can basically turn off the deconfinement transition for these kind of supersymmetric theories. And the fact that you can go to very small radii means that you also come into a regime where semi-classical investigations work and where you have analytic control about the deconfinement transition, and you can derive theoretical predictions. And the question is then, of course, whether you can extend this and learn anything about from this kind of deconfinement transition, calculable deconfinement transitions at small radii about the deconfinement transition in Young's theory. And we have studied this on the lattice as well, and you can see here that the Polyakov loop that indicates the deconfinement transition, if it goes to a non-zero value, you are in the deconfined phase, and you see that it rises for this thermal boundary conditions, but if you switch then to periodic boundary conditions, and if you go to the chiral limit, which represents this blue line here, then basically this transition disappears. At larger masses, we have observed actually two different transitions, which is a little bit different from the picture that I've shown before. And so we have three phases, confined, a deconfined, and then a reconfined phase in these kind of theories. We have later on found that this is basically due to lattice artifacts. You have to take the continuum limit in order to see that this this deconfined phase continues then to the massless limit. And in fact, if you look at the theory at these kind of lattice artifacts, what they do is basically that they add additional fermion flavors to the theory, and therefore you observe this rather different pattern, which as you start here at a certain finite mass, comes from a confined, then a deconfined, and then you end up at a reconfined phase here. In our latest studies,
Georg, maybe I can ask a question.
Yeah.
So, how did you figure out that it was a lattice artifact? I mean, which tools did you use to,
in fact, one can study this even analytically. One can study this down here in the region where you have a small circle, and study this perturbatively even. So here, this kind of range is accessible by perturbative methods, and there you can see that basically you get effectively additional fermion flavors. But in addition, we have also studied in our latest paper more carefully what happens if you go to smaller lattice spacings. So then But as I said, even analytically, one can show that these kind of things appear, and it's basically due to the fact that you have in lattice fermion discretization, you have a larger number of fermions, and you have this additional doubling modes, and these are removed by what is called the Wilson term, which implements an additional mass for these modes. But if you now go to smaller and smaller circle, you probe the theory at higher and higher energies. So you see some effect of these modes if you don't in the same way also decrease the lattice spacing. It's basically just an effect that comes from the fact that your compactification scale reaches the scale that comes closer to the lattice spacing and probes therefore lattice artifacts. Yeah, and just to mention it, we also have now implemented overlap fermions, approximate overlap fermions so far. They are represented by a circle of the eigenvalues of the Dirac operator in the complex space, this Ginzburg-Wilson relation, and you can see here that we have chosen different approximation levels to represent this theory, this overlap gluiness on the lattice. And as I said, in that case, you don't even have to do fine-tuning in order to approach the supersymmetric limit. So what we have to do is we have to extrapolate in our approximation precision instead of having to fine-tune the mass parameter. Yeah, now I think I just briefly mentioned that we also have studied larger number of adjoined flavors. These are studied, and there are basically two different motivations. One is that theories with extended supersymmetry and are including a larger number of fermion flavors. And what you observe is that in that case, you reach quite quickly with adjoined fermions a limit where you are in the so-called conformal window. So where the running of the strong coupling constant changes and you are expected to approach a fixed point in the IR. And the question is now, what can you see on the lattice from this running of the coupling? And we have done investigations of these. There are also other motivations for studying these theories, which comes from the so-called walking technicolor scenario, where you want to implement an additional strongly coupled sector in the standard model. And in order to do this consistently with the experimental, with no conflicts with the experimental data, you need to assume a kind of walking scenario where the coupling constant doesn't really change over a certain longer range of the scale evolution here, of the RG evolution. And in fact, with adjoined fermions, you reach this conformal windows rather quickly compared to fundamental fermions, and even it seems even for two Dirac flavors of adjoined fermions, you are in this case of a conformal, where a conformal fixed point appears in the infrared limit. And so the question is, what happens to n equals 1? So 1 Dirac fermion, and this is interesting because it corresponds to n equals 2 supersymmetric Young's theory without scalar fields. There have been different suggestions for the infrared physics of this theory. It could be that you already see some indications of the conformal infrared fixed point, or you see a normal chirosymmetry breaking scenario. And this has, yeah.
This n equal to 2 supersymmetric Young's theory without scalar fields means that it does not have the supersymmetry. Is that what you somehow drop it by hand, drop the scalars? Yeah,
it's dropped by hand. And the reason is that scalar fields, to implement scalar fields is rather complicated. I will discuss it later. So this is kind of the first step. And one has to study now how close this is related to an infrared conformal theory, because this is, means that the scaling is rather much different, and also that you have different problems if you want to study it on the lattice, because you have to study large volumes in order to get the theory correctly on the lattice.
So, I mean, if I can imagine that somehow I add mass terms to the scalars and lift the scalars to very large masses, then this would be a reasonable comparison. Would it? Because
yes. This is the idea, basically.
Okay.
But the original motivation for the first study that we did, in fact, was rather that we wanted to study this walking technicolor scenarios and see whether if we decrease the number of adjoined flavors, whether we can still see some kind of conformal scenarios. What we have also studied is more recently is then a mixture of adjoined and fundamental flavors. And this corresponds to n equals 1 supersymmetric QCD without scalar fields. So the squawk fields are removed, and then you can study the effect and the interplay of the different fermions. And of course, since you have the gauge fields and their supersymmetric partners, it means you have adjoined fermions. And then in addition, if you want to implement quark fields, you have also the fundamental fermions in the game. And the question is then, as for the n equals 1 cases, how close this is to the conformal theory. And here are just a short presentation of some data here. We have studied this and done some fits according to chiral perturbation theory. Of course, now you have two different mass parameters in the game, not only one mass parameter, and but you can study this dependence and see that it more or less is captured by the data. And then you can also study the conformal scale, compare this to a conformal scaling. You have to take into account now that you in a normal conformal theory, everything would, the masses would scale to 0 in the infrared limit with the same scaling dimension. And here you have to consider now, since you have two different mass parameters, you have to consider two different scaling dimensions. And you can then also try some fits here, but we found that these fits are not really consistent with what one would expect just by, for example, comparing just the scaling with one of the two masses and then comparing the scaling with both masses. So it seems that this theory is rather in a chirosymmetry breaking scenario than a conformal scenario. Now, since we have studied now theories without scalar fields, the question is, why don't we add scalar fields? And there we have to look at the generalization of the tuning approach in 4 dimensions. This means that we have to add all kind of counter terms to the action and tune the parameters in such a way that we can compensate the breaking introduced by the lattice and then arrive at the supersymmetric continuum limit. But if you look at scalar fields, then you get a large number of additional terms that you can construct with these scalar fields. So the tuning becomes very complicated. And so this is, for example, the n equals 1 supersymmetric QCD with scalar fields. So you see that in addition to the ordinary kinetic terms, you have then Yukawa couplings and then phi to the 4 terms, which have a very peculiar structure. And this means, but this specific structure here implemented by supersymmetry has then to be on the lattice to be extended by any kind of breaking parameters, and this means you have a large number of additional terms that you have to tune in order to arrive at the supersymmetric continuum limit. The additional challenges, for example, the scalar potential here has flat directions, so you have a runaway of the scalar fields in the chiral limit, and this makes the simulation even more difficult. But still, there is some progress. There have been first simulations of supersymmetric QCD, and there's also work on perturbative tuning to understand how to tune the parameters in order to achieve the correct continuum limit. Now, as a last thing, I want to discuss also very briefly N=4 supersymmetric gamma theory, which is basically N=1 in 10 dimensions reduced to 4 dimensions. And due to this dimensional reduction, you get this scalar potential that comes from these kind of commutator terms of this scalar fields, which means you have also to deal with flat directions in this theory. It seems that this leads to, again, a very severe fine-tuning problem, but it has been found that you can preserve a kind of subgroup of the supersymmetry algebra on the lattice. This is rather complicated because you have to combine the R symmetry with the Lorentz group, and then you find a certain diagonal subgroup that you can, in such a way that you have fermionic degrees that live on the sides of the lattice and supercharges that act locally on the lattice. And in that way, you have a supercharge that you can preserve on the lattice. But it's only one of these supercharges that you can preserve, and this leads to a much reduced fine-tuning. In fact, it has been observed that there's not really a fine-tuning needed in this theory. And this situation can be compared to the one of the symmetries of space-time, where also a discrete subgroup leads to what is called an accidental symmetry in the continuum limit. So all kind of possible operators are or that can spoil the symmetric continuum limit are already forbidden by the subgroup that is preserved on the lattice. But the simulations with this kind of lattice action are rather challenging. You have a sign problem, you have a complicated lattice structure, and then also, as I said, the flat direction. But from the theoretical point of view, it's also more difficult to understand the continuum limit in this theory, because in QCD, you know very well, because of asymptotic freedom, how the theory should scale to the continuum limit. But here you are expected that the beta function vanishes in the continuum limit, and also the mass anomalous dimension should vanish, and therefore at least for certain operators, and then therefore you are expected to approach some kind of line of fixed points in the infrared limit. And it's very interesting to understand this further and to study this. And therefore, together with David Shake, I've studied a little bit the RG flow using the eigenvalues of the Dirac operator as a probe of the scaling dimension. And here's what we have measured, and what you can see here is that up to small deviation, you see that at smaller Toft couplings, you get almost zero anomalous dimension as expected. But then at larger couplings, you see more considerable deviations from that. In the infrared limit, so if you move further away from the scale where the lattice artifacts are important at higher energy scales, you see that even at larger couplings, this is removed, and you seem to approach this kind of value of zero in the infrared limit. But this gets more and more intricate if you study larger couplings, and this might indicate that you need large volumes and larger scale separations the larger this Toft coupling becomes. So this just illustrates, taking aside also the practical challenges that you have in the simulations of the theory, that there are also theoretical challenges and quite a non-trivial continuum limit of the theory. So that brings me already to my conclusions. I have shown you that supersymmetry on the lattice is still, in some sense, an open theoretical problem, and but for n=1 supersymmetric gamma theory, this supersymmetric continuum limit can be confirmed, and one can use this as a tool to study further properties of the theory. For n=2 superangles and super QCD, this is in 4 dimensions. This is a rather difficult problem, and there's ongoing work, but already for some decades. But it's really a difficult problem, but one can. What I've also tried to show you in a very few slides is that it's even interesting to understand the theories away from the supersymmetric limits. There are related theories in composite Higgs scenarios, etc., that could be interesting to study in parallel to this supersymmetric theories. And I've shown you also that for n=4 superangular theory, there is an alternative approach, but there are still challenges concerning the practical implementation, and then you have to understand also more carefully what happens in the continuum limit of the theory. Okay, thank you for your attention.
Thanks.
Thanks, Georg.
Yeah.
Now it's time for questions from the audience.
Maybe I can ask a question.
Yeah.
It's very vague. I don't know. So you were talking about the reconfined phase.
Yeah.
So for a particular theory, do we have like confined to deconfined to reconfined for a particular theory as we move ahead in temperature? Is it like that for one theory?
This is for a certain mass. So you have to consider a certain mass, and if you consider theories with adjoined fermions, then and not super Young-Mills theory, then even in the continuum, you will have this property. You will have a confined, a deconfined, and a reconfined theory.
Okay.
And a certain mass scale. You can show this even. This has been discussed by Hosotani and others. They've even discussed this as a mechanism to implement some kind of Higgs theories in this regime. Yeah, I mean, there in some theories, this is discussed as a compactified 5th dimensions in some approaches, and there you also are interested in this kind of reconfined theories, or even there are, and if you consider larger NC, there are some intermediate phases that are discussed in this case.
Okay, thank you.
So, and we have seen this on the lattice for superangular theory. This it is expected there's actually no reconfined phase, but due to lattice artifacts, we have kind of additional fermions that sneak in if we are at too small scales of the compactification.
Okay, thank you.
More questions?
So yeah, I had a small thing. So in order to check that you have recovered supersymmetry in the continuum limit, you check for the Ward identity of the super transformations, right?
Yes.
But so supposing you checked only the Ward identity for the translation, would that imply the other one?
No, I mean, the symmetries of space-time can be recovered without supersymmetry here. If we have extended supersymmetry, then there are certain symmetries of space-time that relate part of the supersymmetries with each other.
Oh, I see.
Yeah, but for this n equals 1, so for the particular word identities that we have considered, this is basically only one word identity, and yeah, I mean, you can always try to split the fermion, but since this is a Majorana charge in 4 dimension, there are no way to split them it further. But if you have extended supersymmetry, then there are certain relations between some subsets of these.
I see. So it's not even enough to, so as far as the space-time recovering a continuum limit for the translation operators doesn't tell you anything about whether you have or don't have supersymmetry.
I would say that you need to have intact symmetries of space-time, but this is not sufficient to have supersymmetry. Yeah, the symmetries of space-time, as I said, they can be guaranteed by this subgroup, this lattice subgroup of that is restored, that is intact on the lattice. But for supersymmetry, you can write down a lot of additional terms that don't violate the symmetries of space-time, but violate supersymmetry.
Okay, I understood. Thank you. Thank you. Thank you for a nice talk.
More questions? So Georg, maybe I can ask one question. So this question is about the free energy, the 3×4 problem in n equal to 4 superangles. So how easy or how difficult it is to simulate on the lattice? Have you thought about that?
What kind of thing?
It's the 3×4 problem where people have computed the free energy using perturbative calculations in field theory, n equal to 4 superangles, and another calculation in holography, and they are not matching.
Okay, yeah, I mean, this requires first to have the n equals 4 super Young-Mills theory under control in the simulations. And I think you also know that yeah, one first needs to investigate even at stronger couplings, right, this kind of theory. And I'm more concerned at the moment to understand how the continuum limit is approached and whether this is correctly represented, then how one can implement then this additional question. There are a lot of additional things. I mean, there have been suggestions by Joel Yeat to study the S-duality, etc. There are a lot of interesting questions that one can study, but of course one has to understand also how the theory behaves. And yeah, I'm not sure whether it's enough, whether the current range of couplings are enough to answer these questions.
Okay. Okay, so it seems like there are no further questions. So let's thank Georg again for a nice talk. Okay, thank you everyone. So
thanks again.
Yeah, thanks Georg. Hopefully, we will see you in one of the upcoming meetings in person.
Yeah, of course. Of course.
Lattice 2022 is